G'day legends, welcome back to the channel for our last integration video. Today we're starting off with a flashback to last lesson. If you've already watched that video, by all means pause and have a go at these two integrals and let's see if my answer is the same as yours. Okay, cool. So for the first one, we're going to be applying integration by parts because we have a product of two functions. We've just got to figure out which one we want to differentiate and which one we want to integrate. So because log x is pretty hard to integrate, that's the half that we are going to differentiate, which we call u. And so x to the 7 is going to be our thing we're going to integrate, which we call v prime. All right, so differentiating log x, we get 1 over x, and integrating x to the 7, we get x to the 8 over 8. Now we apply our by parts formula from last video. So we've got uv at the front, so log x, x to the 8 over 8. And don't forget, when your integral has limits, your uv at the front, you need to apply the limits as you've just integrated this. Okay, then we take away the integral of the bottom row, which is u dash v, which we can see right here. Okay, subbing in our values, when we sub in e, we're going to get e to the 8 over 8, and log of e is equal to 1, so we end up with e to the 8 over 8. Fortunately, when we sub in 1, log of 1 is just 0, so the whole thing turns into 0, so we get e to the 8 over 8. Now for our integral, we can pull the 1 over 8 out the front as a constant, and the x on the bottom cancels with 1 on the top, leaving us with x to the 7. Now we have a really easy integral to evaluate. We're going to raise the power to 8, divide by the new power of 8, and sub in our two limits. That's the hard work done. Now we just sub in the numbers, and we end up with e to the 8 over 8 minus 1 over 8. When we expand everything and fully simplify it as one fraction, we end up with something along the lines of 7e to the 8 plus 1 over 64 as our final answer. Now over on the right, we have the integral of t times e to the t squared. So it kind of looks like a question where you could apply integration by parts because we have a product of two functions. However, if you take a closer look, we can actually either use a substitution or apply the reverse chain rule. So if we had if we had a 2 here, we would have 2t times e to the t squared. So we've got a function multiplied by its derivative. So if you're really good at the reverse chain rule, you can use that, or another option is to use a substitution. We can let u equal to t squared. So du on dt is 2t. Swapping these two out, we get du over 2t equal to dt. Subbing all this information into our integral, we end up with integral of t, e to the u, and our dt is du on 2t. The t's cancel out, we put the half out the front, and then we integrate e to the u to become e to the u. We add our constant and then we back substitute the fact that u is of course t squared to get our final answer. So no integration by parts needed. Always keep an eye out for either the reverse chain rule or substitution because they are a bit quicker and easier usually. Okay, for our final integration lesson on this channel, we are looking at what's called recurrence relations, also known as simple reduction formula. This is a very challenging lesson in my opinion. This is one of the hardest parts of the Extension 2 course. These questions from exams typically always hit band 5, 6, so a lot of people struggling with these. So I'll go as slow as I can. We're going to go through 5 examples today to give you a good idea of how these things work. But yeah, as you'll see, these are quite tough. Okay, here's the first one. This is one of the easy ones that I could find. It's from the 2012 HSC. We have the integral with a label of n is from 1 to e squared of log base e, which is the same thing as ln x to the power of n. Okay, so that power of n corresponds with the label on our integral. So for example, in part B, when we find I3, we're going to find this integral with a power of 3. So to get I3, they've given us what's called a reduction formula, which is a formula linking a power of our integral with one step below. We're going to attempt to prove this formula so we can then use it to find I3 in part B. So for questions like these, 9 times out of 10 in the HSC, they are going to involve an application of integration by parts. So if you're not sure where to start, that's usually going to be a good guess. So for this one, it doesn't look like we have a product to apply integration by parts unless you imagine there is a 1 here and we've got 1 times ln x to the power of n. That's our product and we are going to use integration by parts. We're going to set log base e of x as the thing we're going to differentiate because obviously that's very hard to integrate. And the invisible 1 at the front is the thing that we are going to integrate, which is nice and easy. So if we differentiate our u using the chain rule, the n comes down, we have a power of n minus 1, and now we multiply by the derivative of what's inside our bracket, and the derivative of log x is 1 over x. So there's our u dash. If we integrate 1, we of course get x. This is the information we're going to substitute into our integration by parts formula, so which looks like this. At the front we have uv, so we have log x to the n times 1, times x. And we've got our limits of the same thing as the start between 1 and e squared. Then we take away the integral of the bottom row, which is u dash v. So we've got our derivative of log x multiplied by x, which looks a bit messy, but these things always tidy up nicely if you proceed correctly. Okay, when we sub in our values, when we sub in e squared, we get e squared log of e squared to the power of n. Fortunately, again, like from the flashback, when we sub in 1, we get log of 1, which is 0. So the second half of our limits are just invisible. We don't need to worry about them. Okay, hopefully you are aware that log of e is equal to 1. So log of e squared, that 2 comes down the front and becomes a 2. So log of e squared works out to be 2. So we get 2 to the power of n at the front, which, looking at our target, is good news because that's what we were aiming for. Okay, for our integral, we pull the constant n out the front, and the 1 over x and the x cancel each other out, and we're left with log of x to the power of n minus 1. Now, looking at where we started, this was our label for integral with the power of n. And what we've ended up here is the exact same integral, the exact same limits, the exact same thing inside the bracket, except now our power is n minus 1 instead of n. This means what we're left with on the end here is the integral of n minus 1. Okay, so the label at the bottom corresponds to the power in the question. So there we have our required answer. Like I said, this turns into 2, so we get 2 to the n, and this is just an expression for integral of n minus 1 with an n out the front, and that's what we were asked to find. Okay, hopefully that made some sense. I do need to skip a few steps in these solutions just to fit it all on one slide, so apologies if this is a bit quick, but yeah, this is a very high level of difficulty in a lot of these questions. So there's part A done. Now the good news about these questions is that often if you can't do part A, which is often the challenging part, there's nothing stopping you from using this formula and continuing on with part B. Okay, so just because you can't derive this formula, you can still use it and get some marks from the question. Okay, we are going to find the integral with the power of 3. What we're going to do is we're going to start with the smallest possible power, which is I0. Okay, I find these questions easier if you start with the easy integral and you work your way up to the target. So I of 0, when the power is 0, log x to the power of 0 is just 1. Okay, so then when we integrate 1, it turns into x. Okay, so inside the bracket, power of 0 is 1, integrates to x, we apply our limits, and we get e squared minus 1. Now that's I0. Now using our recurrence formula, if we have I0, we can use this to calculate the next step up, which is I1. Okay, so applying our formula, I1 is e squared 2 to the 1, take away 1 lot of I0. So that right there is us applying our reduction formula. So we have 2e squared at the front. We're taking away I0, which we just found to be e squared minus 1. If we expand and simplify this, we end up with e squared plus 1 as our answer for I1. Okay, a couple more steps. Now we use I1 to build up to I2. So once again, using our formula, replacing n with 2. And so n minus 1 is 1. Okay, at the front we get 4e squared, and then we're subtracting 2 lots of I1, which we just figured out to be e squared plus 1. Again, if we expand and simplify this, we end up with 2e squared minus 2 as our expression for I2. All right, and last step, we use this to build up to I3. So using our recurrence formula with n being 3. So we have 3 times I2 on the end. So we get 8e squared at the front, take away 3 lots of our previous answer. Expand, simplify, and we end up with 2e squared plus 6 as our final answer for I3. So these 4 steps weren't super difficult, and like I said, even if we hadn't done part A, we could have just started here and we would have got a couple of marks sometimes. Okay, so don't give up if you can't do part A. Keep going, grab some marks, and kick on. Okay, moving on to example 2, a bit of a tougher one now. We have our integral with a power of n is cos to the nx between 0 and pi on 2. The recurrence formula we want to try and prove is that in is n minus 1 over n, and we've got multiplied by I of 2 steps below. Okay, this one's got a bit of a trick to it because we want to prove a formula that's involving a power of n minus 2 rather than n minus 1. So if we think about differentiating cos to the power of n, if we bring the n out the front, the power is going to reduce to n minus 1, which is not going to be much use to us because we want to end up with an expression involving a power of n minus 2. That's why the trick for this question is to re-express our integral like this. We're going to split the coses apart as cos to the 1 multiplied by cos to the n minus 1. This is really clever because now when we differentiate cos to the n minus 1, we'll bring the n minus 1 down the front and the power will become n minus 2, which is what we're trying to prove in our result. So this is our product. We are going to differentiate cos to the n minus 1, and so we're applying integration by parts, which means we need to integrate the other half, which is cos x. So we're setting that as our u, and we're setting cos x as our v prime. Okay, differentiating cos to the n minus 1 using the chain rule. So n minus 1 comes down the front. Power is now n minus 2, and now we need to multiply by the derivative of cos, which is negative sine. Okay, so applying the chain rule here, integrating from v prime to v, the integral of cos is sine. So here are the pieces we need for our by parts formula, so let's chuck those in. So at the front we have our, what do we got? Our uv. So we've got our cos to the n minus 1 multiplied by our sine. Limits, same from the question, are between 0 and pi on 2. Take away the integral of, we got u prime times v right here. Okay, so we've got our expression that we differentiated for u prime floating around here, and this is being multiplied by v, which is our sine x, so right there. Okay, so we're going to tie this up as best we can. At the front, when we sub in our limits, fortunately, well, what's fortunate? Fortunately, sine of 0 is equal to 0, so it's going to vanish away. And also fortunately, cos of pi on 2, which is cos 90, is also equal to 0. So when we sub in these two values, both of our answers turn into 0, which means we can just leave this blank. Okay, we'll pull the n minus 1 out the front of the second integral. We've got a negative sign somewhere in the mix, which is going to make the negative out the front go positive. That's good. And we've got a sine times a sine, so we've got sine squared, and we have cos to the n minus 2x dx. So inside here is the integral that we want, except we don't want the sine squared in here, we just want the cos to the power of n minus 2. So we're going to have to do something clever again. We need to express sine squared in terms of cos squared because we're trying to get an integral only involving cos. So that's our next step. We're going to write sine squared as 1 minus cos squared. Now this next bit can be a bit tricky to see, but what we're going to do is we're going to split apart this integral where one of them is going to be, essentially we're expanding out this bracket. So one of our integrals is going to be cos to the n minus 2 times 1. The other one is going to be cos to the n minus 2 times cos squared. Okay, so expanding out this bracket and then splitting apart the integral. We're doing it in one step because again, we're trying to save time on my small screen. Okay, expanding out our integrals and splitting them apart, we need to keep that n minus 1 out the front because it's a constant out the front of the entire thing. So here is our cos n to the n minus 2 multiplied by 1. And here is our cos to the n minus 2 multiplied by cos squared. When we multiply these two and we add the powers together, n minus 2 plus 2 gets us back to n. Okay, so it looks like we've made it more complicated, except now we have two integrals that are only involving cos, which was the definition of our integral with a base of n. So we can now write these in terms of our original notation, okay? On the end here, we have in, and in the middle here, we have in minus 2, which is what we were trying to get at the target. Okay, so writing it in terms of that, we have n minus 1. So on the left, we still have the starting integral, which is in. We have n minus 1 times I of n minus 2. Take away n minus 1 of in. Now we need to do a bit of collecting. We're going to put the in's together on the left-hand side. So we're going to add this across. Now we're going to factorize the left-hand side. So we're going to pull out a common factor of in, which leaves us with 1 here and then n minus 1 here. Okay, so left-hand side just factorized, which is convenient because 1 minus 1 is just 0. So on the left-hand side, we just have n. We can divide that n across the other side, and there we have our target from the question up in the right-hand corner. Okay, so pretty tricky. A question like this I had to do a few times before I felt really comfortable doing it from start because of the splitting apart and all the, just the complicated rearrangement of the integrals. But yeah, this is extension 2, mate. It's pretty tough. All right, there is our part A achieved. Now we can apply part B, which is finding the value of cos to the power of 5, which is I5. Okay, so as we already noticed, this integral is stepping up in powers 2 at a time. So we're going from n minus 2 up to n. So to find I5, we need to find I3. And to find I3, we need to find I1. So there is our starting point. We're finding I1, which is just the integral from 0 to pi on 2 of cos x. Cos integrates to sine, and when we evaluate our powers, our limits, we get sine of 90, which is just equal to 1, and sine of 0 is equal to 0. So we just get 1 as our answer here. Okay, there's I1. Now we can apply our reduction formula or our recurrence relation to build up from I1 up to I3 because we're going 2 steps at a time. So we have I3 is 3 minus 1 over 3 multiplied by I of 3 minus 2, which is I1. Okay, cool. So that gives us 2/3 times I1, which was 1. So we end up with 2/3. Now our last step is to get from I3 to I5 using our formula. So I5 is 5 minus 1 divided by 5 multiplied by I3, which is equal to 2/3. So we get 4/5 times 2/3, and we get our final answer of 8/15. So there we go. We do the hard work at the start, so then the formula just spits out nice answers for us without having to do any integration. All right, groovy. On to example 3, which is probably the most gnarly. So we'll see how we go. Okay, our recurrence relation is whatever the label and our integral, we have x to that power times the square root of 1 minus x dx, integrating between 0 and 1. Here is our recurrence relation that we are trying to achieve. So let's just dive right in with some integration by parts once again. Okay, so looking at our two pieces of our integral, we are going to say, well, I want to bring the power from n down to n minus 1. So hopefully it's kind of obvious, or maybe apparent, that x to the n is the thing that we want to differentiate. That unfortunately means we need to integrate the square root of 1 minus x, which is not impossible. It's just a bit messy, but I mean, we've dealt with worse before. So we're setting x to the n as our thing to differentiate. And so we're going to write 1 minus x to the power of the half as our thing to integrate. X to the n differentiates to nx to the n minus 1. And if we integrate this, we've got to apply the reverse chain rule. So we are adding 1 to the power to become 3 over 2. We're then dividing by 3 over 2, which puts that 2 actually up the top. Okay, so when you divide by a fraction, the very bottom of the fraction just flips up top. And on the bottom, we need to divide by the derivative of what's inside our bracket, which is just -1. So that's why there's a -3 on the bottom, not a +3. Okay, there's our pieces for our integration by parts. So let's apply that now. So yeah, it's pretty hectic. So we've got uv at the front. So u times v just here. Just writing the power of 3 over 2 as the square root cubed to make the substitution a little bit easier. Going between 1 and 0, and then minus the integral of the bottom row, which is u dash v. So we've got the nx to the n minus 1 multiplied by our integral of v dash. Okay, and hopefully you already know that when you've got a cubic, you can either put it inside the square root or you can put it outside, whatever is more convenient. So both of these are saying the same thing, just in different ways. Okay, tidying up as best we can. So at the front, when we sub in 0, luckily 0 to the power of n is nothing, so the front just vanishes. And when we sub in 1 inside our square root, we get the square root of 0 cubed. So just like last time, both of our limits in the front give us answers of 0, so we can just leave that blank, essentially. Okay, we will pull the -2/3 n out the front of our integral, which makes positive 2n on 3 out the front. Now we have x to the n minus 1, and for this question, a clever way of writing the square root of 1 minus x cubed is to think of this as 1 minus x square root times root 1 minus x times root 1 minus x. So because you've got two square roots of 1 minus x multiplying, they're going to turn into a 1 minus x and leave you with 1 left over square root of 1 minus x. Okay, so if you can't see the jump from here to here, just write this out as a power of 3 by multiplying 3 times, and you'll see 2 of the square roots cancelling out, leaving you with this. Okay, that's a bit hectic, and now we're going to do the same thing we did last question, where we're going to expand out this bracket with 1 minus x, and we're going to split apart into two integrals. So this is the part where it gets a bit hairy, but try and stay with me here. So multiplying this integral by 1 is right here, and then multiplying this integral by negative x is right here. Okay, so got the same thing at the front, just multiplied by 1. And then when we multiply by x, x to the 1 times x to the n minus 1 leaves us with x to the n, which is good because this is now all in terms of what we started off with. Okay, so we're trying to rearrange our resulting integral so that it looks like the recurrence relation starting point. Okay, so right here we have our starting integral with a power of n minus 1, and on the end we have our starting integral with a power of n. So we can write this in terms of our notation from the question. So we can write this as I of n minus 1, and we can write this as I of n. Okay, don't forget on the left-hand side, we still have in. So now we're going to do a bit of algebra to collect the in's together over on the left-hand side. So we have in plus 2n on 3 in. We are going to factorize the left-hand side like this. So we have 1 plus 2n on 3 multiplied by in. We're going to divide this across to make in the subject. And then to finish it off, we're just going to take this fraction and we're going to multiply top and bottom by 3. So we get 2n on the top, and on the bottom we get 2n plus 3. And that is the target that we were asked to prove in the question. So yeah, some pretty hectic algebra, a lot of surds, a lot of expanding, a lot of powers, but hopefully you kept up with that. Or if not, let's just dive on to the next part where we can actually use this formula to evaluate some integrals. So there is our formula. Part 2 is find I3 and show that it is 32 over 315. So to get I3, we need I2. To get I2, we need I1. And so to start off with, we are going to find I0 so we can find I1 using our recurrence formula. So yeah, always start with the easiest integral and then build up is probably the best way to do these. Okay, so I0, x to the 0 is just equal to 1. So we are just integrating the square root of 1 minus x, which we've already done today, so we can do that pretty quickly. Same result as before, subbing in 1 and 0. When we sub in 1, we're expecting to get 0 like we did before. When we sub in 0, we get 1 minus 0, so we're doing the square root of 1 cubed. So this just turns into 1 on the top. And so we have 1 divided by negative 3 over 2, which is negative 2/3. Okay, so applying our integration for I0, we end up with negative 2/3. That's now the integration done. We can now use I0 to get I1. So I1 is going to be 2 times 1 over 2 times 1 plus 3, and multiplying that by I of 1 degree less, which is I0. Okay, running through this pretty quickly now, because this is the easy part. We apply our formula and we end up with negative 2/15. Now we use that value to find I2. So we've got 4 over 4 plus 3 multiplied by our previous answer, which was negative 2/15. That works out to be negative 8 over 105. And now to finish off, we use I2 to get our value for I3. So we get 6 over 9 times I2, which is not the answer in the question. Oh my God, that sucks. Let me just... Okay, so I figured it out. Turns out I was actually away the day in year 1 when we did 2 times tables, so I forgot that 2 times 2 is actually 4, not 2. So this answer gets doubled, this answer gets doubled, and then my final answer gets doubled, so I get 32 on the top and not 16, which is the answer we were told to get in the question. So there we go, we did it. As long as you remember your times tables, unlike me, you should be fine with this question. All right, let's move on to example 4. Okay, we've got our integral of subscript n is from 0 to 1 of x to the 2n plus 1 multiplied by e to the x squared. Starting off with our recurrence relation, we're trying to show that this is the formula relating integral n with integral n minus 1. Okay, so straight away, just going to apply some integration by parts. However, a bit of a sneaky one, because looking at the integral, the thing we want to differentiate is the x to the 2n plus 1, because we want to bring down the power, so we end up with an integral of n minus 1. The issue with that is that if we want to differentiate x to the 2n plus 1, we're going to have to integrate e to the x squared, which is very, very hard to do. So the sneaky way to rewrite this question to make it much, much more doable is like this. We're going to split apart the x to the 2n plus 1 as x to the 2n times x to the 1. Okay, the reason this is really clever is because now x times e to the x squared is very easy to integrate by using the reverse chain rule. Okay, so splitting these two apart, and now this is the part we're going to differentiate, and this is the part we're going to integrate. Okay, so setting u as x to the 2n, which means we're setting our antiderivative as x e to the x squared. Differentiating our u, we have the 2n coming down the front, and now we have a power of 2n minus 1. Now, I'm going to go over this briefly, but if this was a 2x in front of the e to the x squared, 2x is the derivative of x squared, so we can apply the reverse chain rule. So if I wanted to integrate this, I'd put a 2 at the front here, which means there'd be a half at the front of the integral, and then applying the reverse chain rule, we get a half e to the x squared. Okay, if that's a bit too quick for you, just check by differentiating this and you'll end up with v dash just here. But there is our setup for us to do integration by parts, and this one actually works out pretty nice and quick. So here is our integration by parts. At the front we have uv, so we've got x to the 2n with our half e to the x squared. So we have our uv at the front, our limits are 1 and 0, and then we have the integral of the lower level, which is 2n x to the 2n minus 1, multiplied by half e to the x squared. Okay, tidying this all up. So when we sub in 1 into here, we get 1 times a half of e to the 1. So when we sub in 1, we end up with a final answer of e over 2. Okay, because we get 1 here and we get e over 2 here. Luckily, when we sub in 0, anything to the power of, 0 to the power of anything is always 0, so our second limit is non-existent. So the front term just works out to be e over 2. Okay, inside our integral, we have 2 times a half, which is going to make a nice easy 1. We're going to pull the n out the front of the integral, and then what we have here is x to the 2n minus 1 times e to the x squared. And if we wanted to check this by taking out the 2 here, we would get that this is actually the integral of n minus 1. Okay, so in very quick steps, if we use the correct integration by parts with this clever splitting up, we get to the target relatively quickly. And here's just the proof that if we split this apart, so we have 2 times n minus 1 plus 1. If we expanded this power, we'd get 2n minus 2 plus 1, which would work out to be 2n minus 1. This is just me showing you really clearly that now the target that we have achieved is the integral, the starting integral, the exact same thing, except the n is now an n minus 1. So we can rewrite this integral as I of n minus 1. Okay, so there we have our recurrence relation proven through the magic of integration by parts. Now we can actually use it. So for part B, we're going to calculate I2. So to do that, we'll start with I0, which is our original integral, but with an n being 0, so we get an x to the 1 here. Okay, this is something we've already integrated in this example. We can do it nice and easy, and it's going to turn into a half e to the x squared. Okay, there's the long version. You put the 2 there, you put the half out the front, and now 2x is the derivative of x squared. Applying the reverse chain rule, we get just e to the x squared. You can put the half inside, you can put the half outside, whatever you're in the mood for. Our limits are 1 and 0, so we're going to get e to the 1, take away e to the 0. Okay, e to the 1 is of course e, so we get e over 2, and e to the 0 is 1, so we get 1 over 2. So there is our first integral evaluated. There's I subscript 0. Now we can use our recurrence relation, or we can even put this together as one fraction as e minus 1 over 2. Okay, using our recurrence relation, so we're using the fact that I1 is going to be e over 2 minus 1 times I of 1 less power, so I0. Okay, so we're using our recurrence relation, starting with I0 inside the formula to get us I1. Okay, I0 from before, we just calculated this, that's e minus 1 over 2, so I'm going to sub this into here for I0. So we have e, take away e minus 1 over 2. The 2 e's cancel out and we get minus 1, so we end up with just positive 1 over 2. Okay, nice and simple. Now we use I1 to build up to I2 using our recurrence relation. So I2 is going to be e over 2 minus 2 times I of 2 minus 1. Okay, I1 we just calculated to be a half, so we end up with e over 2, take away 2 lots of a half, which is just 1. So we end up with a final answer of e over 2 minus 1. All right, cool, we're getting there. I think that's the end. One more example, all right? This is an example from the 2016 HSC exam. I wanted to end on this one because this is a recurrence relation type question that doesn't actually involve integration by parts, but it's still using the subscript notation, and it applies it to a lot of different methods of trigonometry. So this is a pretty big question, a lot of marks. Let's dive in. First part, here's our integral. We want to show that I0 is equal to pi over 8 plus 1 over 4, and it's hinting that we should use a suitable substitution. So let's have a look at what I0 looks like. So taking our formula from the question and replacing the n with a 0. So we have x to the 0, which is 1. So now we've got to stare at this integral and we've got to think, all right, what's a clever substitution that's going to allow us to integrate this efficiently? So hopefully you may have already covered or may have already watched my video on trig substitutions. In that video, I detailed how when part of your integral is x squared plus 1, in this circumstance, a really clever substitution to make is x equal to tan theta, because inside this bracket, we're going to get tan squared plus 1, which is a trigonometric identity. Okay, so the question is hinting for you to know that in this integral, we can let x equal tan theta, and it's going to work out really nicely. So we'll do our dx, so the derivative of x is equal to sec squared d theta. That's going to be substituted in for dx on the end. We'll very quickly change our limits. So when x is equal to 0, tan of 0 gets us 0, so the 0 doesn't change. When x is equal to 1, tan theta equal 1, the first solution for this is 45 degrees, aka pi on 4 radians. So our two limits are changing from 0 and 1 to 0 and pi on 4. Our dx is changing to sec squared d theta, and our x squared is going to turn into a tan squared. So let's see what that looks like. It looks like this. Oh, so beautiful. All right. So on the bottom, hopefully we know that tan squared plus 1, that's a man and a tan, that is sexy. So 1 plus tan squared is equal to sec squared. However, this bracket is being squared, so we have sec squared squared, so we have sec to the power of 4. Okay, so sec squareds cancel out on top and bottom and leave us with 1 over sec squared. And of course, 1 over sec is cos, so this turns into cos squared d theta. Okay, we know how to integrate cos squared from the extension 1 course. The substitution is on your reference sheet if you forget. Here is our substitution for cos squared that is much more integratable. Let's chuck that up here now. Okay, so we can just leave the half at the front for now. The 1 turns into a theta, and the cos 2 theta integrates into a sine 2 theta divided by 2. There's the calculus done. Let's chuck in some limits. So subbing in pi on 4. Okay, so when we sub in pi on 4, we get pi on 4 plus a half of sine of 90. And keep in mind that sine 90 is 1. Okay, so this half is just a half times sine 90. Half times 1 gets you a half. So the pi on 4 and the half is the first limit. Luckily, the second limit, we just get a 0 here, and sine of 0 is 0. So the second limit in the integration just gives you an answer of 0. Okay, if we expand this out, we get a half times pi on 4, which is pi on 8, and a half times a half, which is a quarter, which is the target from the question. So there we go. So the content knowledge you need in the back of your mind to get this question achieved is that the substitution to make was x equal tan theta, which is why this is more of a challenging question. But there we go, we did part A. Now part B, show that I0 plus I2 is equal to pi on 4. So let's go to our integral and let's have a look at I0 and have a look at I2. This is what they look like, okay? This is I0 again from part A, but we haven't integrated it yet. And here is I2. The power on the top of the fraction is x squared. Now, it is tempting to sub in the fact that we know what this front part is equal to from part A. We're going to ignore that temptation and we're going to actually combine these two integrals together because that's the easier way to achieve this question. So we've got dx, we've got the same limits, and the same base. So we can combine these two integrals by just adding our numerators. So we're going to have 1 plus x squared on the top of the fraction, all combined as one juicy, beautiful integral. Now, why this is so convenient is because now we have an x squared plus 1 on the top and bottom of the fraction, and so we can cancel them off the top and bottom, leaving us with 1 over x squared plus 1, which is a very doable integration. Okay, we can do this by using inverse tan from the extension 1 course. So the integral of 1 over x squared plus 1 is just inverse tan of x. Subbing in our limits of 1 and 0, tan inverse of 1 is just equal to pi on 4, and tan inverse of 0 is just 0. So there we go. We have shown that I0 plus I2 is equal to pi on 4 as requested. And now the spicy part to finish off is find the value of I4. So let's go back to our integral and let's change the n to a 4. And we've got to think of a clever way of evaluating this integral. Okay, the clever method here is using something I did in a video a long time ago, which is called splitting the numerator. what we're going to do is we're going to add to the top and bottom a -1 and a +1. So we've added 0 to the top of the fraction. It's still the same integral, but now we're going to split this apart into two separate integrals. So we're going to leave the x to the 4 minus 1 just here. We're going to split apart the +1 into a separate fraction and a separate integral. Okay, because this part on the end, we already know what the value of this is. We already figured this out in the earlier part of the question. Now, the reason we wanted x to the power of 4 minus 1 here is because this is a really convenient difference of two squares. We can factorize this as x squared minus 1 and x squared plus 1, and x squared plus 1 is on the bottom of the fraction, so it's all coming together. This is absolute poetry. So the bit on the end is I0. Well, we can sub that in because we have the answer to that from part A. Cool little voice crack there. Okay, for our first fraction, like I said, we have an x squared plus 1 on the top and bottom. We can cancel those out, and it looks like this. Okay, we have an x squared minus 1 still chilling on the top. On the bottom, one of the x squared plus 1s has vanished away, and now we have this. So we're not done yet. We're now going to do another clever little splitting the integral here by making the top a +1 and then taking away 2. Okay, so we're very cleverly writing -1 as +1 take away 2. Okay, because then we're going to split apart this integral again. Two splits in one question. This is so much fun. So splitting apart this, we'll leave the x squared plus 1 in the first fraction. We'll take away 2 on the top of the second fraction. And don't forget, you've still got an I0 chilling on the end, but we already know the answer to that, so don't stress. Okay, now this is looking good because the front fraction, or the front integral, is just the integral of 1, which is super easy to integrate. And then we have take away 2 times 1 over x squared plus 1, which again, we've already done. This can be achieved using inverse tan. So we keep splitting it apart until we get down to stuff that's easy to integrate. And now we kick on and do some calculus. Okay, so like I said, this fraction turns into 1. When we integrate it, 1 integrates into x, and we have our limits of 1 and 0. We can pull the 2 out the front of this integral, and then we have 1 over x squared plus 1, which we integrate using inverse tan, like from before, and we still have our limits of 1 and 0. Now we just got to sub in and tidy it up. So we're going to get 1 minus 0 at the front, which is going to be 1. We're going to get tan inverse of 1, which is pi on 4, and tan inverse of 0, which is 0. So when we do all the maths, we end up with 1 at the front. We get 2 times pi on 4 in the middle, and I0 from part A is pi on 8 plus plus 1 on 4. Tidy it all up, and we end up with 5/4 take away 3 pi on 8, and there is your full marks answer from this very challenging question from the 2016 HSC. Okay, there's one more question for this video, but it is left as an exercise to the reader because this video is already super long, and this is kind of similar to one of the examples we did earlier in the video. So if this is making sense, by all means, pause and have a go. If you want to look up the solution, it's from the 2020 NASA sample exam. You can Google that and see the solution and see if you're on the right track. But that'll do it for today's video and integration. So thank you so much if you made it this far. And thanks heaps for getting the channel up to 600 subscribers. That's awesome. Onwards to 1,000. Okay, look forward to some mechanics videos over the next term on this channel, and then we'll have extension 2 all wrapped up. So that'll be heaps mad. All right, cool. Thank you for watching, and see you in the next video. Bye, legends.